Hello and welcome to the second video. In this video, I'm going to show you how to run a simulation. So if you read the paper that these videos are a part of it, you'll realize that we have 5 different test cases. The setup process, including the generation of the input files, the setting up of the simulation and running it, is almost the same for all of them. But 2 of the test cases have exclusive requirements and technicalities, and therefore I'm just gonna cover those 2, and if you understand what to do with them, you can easily run the other simulations. So in this video, I'm going to focus on the UpperLEE. UpperLEE is a real-world pluvial flooding scenario which happened in 2014 in catchment in North London called UpperLEE, and it is a pluvial test case, so it means that it is featured by rainfall data, and it also has a map of land use which has like 7 classes of Manning coefficient. So to get to know this test case, I'm gonna start with the input files that we have in the beginning. The first input file is a DEM file with 20-meter resolution, which is saved in a ASCII format. So if we open it using a simple text file editor like Notepad++, we'll see that this is a structure of the ASCII file, and this is the header saying that okay, this is the 20-meter resolution, number of columns, number of rows. So it's pretty much simple. We can load this raster file in a QGIS software. So if I open it in QGIS, this shows the map with the variation of the topography from 18 to 200. The second file is the land use map, which is also a raster file, and it's saved in a file with the same name and extension of .n. So if I open it in Notepad++, it shows that it's following the same structure of the raster file as the DEM file, and I can even open it in QGIS. So if I open it in QGIS, this shows the variation and the different classes of Manning, each related to a value for the Manning coefficient. The other data that we have for this test case is the rainfall data, and for this test case, the rainfall is given as spatially and temporally varying data, and is saved in a .netcdf file format with the extension of .nc. So if we want to visualize the netcdf file, we can load it in QGIS. And initially it's just shown in this weird snapshot. But if we click on the layers and from the symbology menu select single band pseudo color, in the band menu we'll see the different time steps of the rainfall data, ranging from 0 hour all the way down to 120, which is the time of simulation and the length of the rainfall data. So if I click on a snapshot or time step of, for example, 50 hours, and I click on apply and OK, this shows the spatial variation of the rainfall data on the time step of 50 hours. And these are the actual values of rainfall data in each different cells or pixels of the rainfall data that covers all the catchment. We have another data, which is the initial condition for the water depths, because this test case starts from a wet condition, so that all the rivers are initially full. So for defining the water depths, the initial water depths, we need a file named with the extension of .start. So the name is the same as the other files, but the extension is .start, and it's the same format of the raster file. If I open it in Notepad+, you'll see that, okay, these are the values of the initial water depths with the same format of the DEM file. I can open this file in QGIS. So this is going to be the values of the initial water depths. You can see that it varies between 0 and 5. The last input file that we have for this test case is the .stage file, which specifies the position of the staging point, or the points that we're going to record the water depths or velocity during the simulation. So it has this one, it only has one point for recording the values, and these are the x and y coordinates of that certain position of the staging point. So after preparing and setting all these input data, we need to set the simulation setup parameters in the .par file. So if I open the .par file, you'll see that many of these keywords are familiar for you if you know how to run lisflood, the original version of lisflood. So most of them are just referring to the related input files, like the dynamic range or the names of the directories. This is, for example, the simulation time or the initial time step, the intervals of writing the staging point files and the 2D output files. The only new parameters or keywords that we are setting here is the combination of ACC underscore non-uniform grid and the CUDA. So if you want to set the non-uniform ACC solver for the simulation, because it only comes with the GPU parallelized version, we should include both of these keywords for activating the CUDA or the GPU parallelized version and selecting the non-uniform grid. The other new parameters are the epsilon and L, which refer to the adaptivity threshold parameter and the maximum resolution level, which if you read the paper, you'll know what these two parameters mean. The next step that we need to do before running the simulation is to generate the DEM files, because if you read the paper, you'd know that the non-uniform grid generator that we use relies on 3 different DEM files instead of only one. So the raw DEM file is a raster file that demonstrates or shows the topography variation as piecewise constant data. But for the generation of the non-uniform grid, we need to reshape or reconstruct or redefine this DEM, piecewise constant DEM, into 3 files, one containing the average coefficients and 2 containing the slopes in X and Y direction. To understand the theory behind this DEM generation and the use of the 3 DEM files, you can read the paper that we published on the previous version of lisflood-fp, which covers the whole process of the generation and the need to have the 3 DEM files. So to generate these DEM files, and of course to run the code, we need to get the executable and put them in this the same directory that we have the input files, because that's probably the most straightforward way to run the simulation and makes all our other directories independent of each other. So to do that, I'll go to the directory that I've installed lisflood-fp, and in the directory output, out, and then in build, and MSVC x64, I'm going to select all the executables and the DLL files. I'm going to select all of them and copy to the directory that I'm going to run the simulation from. So I'll put it and put all these files in the UpperLEE directory. I don't need this file, so I'm going to remove it. So once I have all the executables and the DLL files, I can launch any of these. So the preprocessor file or preprocessor executable that I need to generate the DEM, the 3 DEM files, is called generate dg2 DEM. So to run that preprocessor toolbox, I will need to click on the address bar, type cmd, and this will open the Windows command line. And after that, I need to type the name of the generator file. So it will be generate dg2dem.exe, and after that I need to specify the name of the .par file, which is UpperLEE 20meter.par. So now if I click and enter, the preprocessor would start working, and after that we'll see that the 3 DEM files would be generated. So this is our the main raw DEM file, and after the preprocessor finishes running, there will be 3 files generated. .dem is the DEM file for the average coefficient, and DEM1x and 1y are the slopes of the DEM in x and y direction. After I run the preprocessor and generate these DEM files, I'm ready to run the simulation. And to run the simulation, I'm going to use the same CMD window and run lisflood. So I'm going to put the name of the lisflood executable, which is lisflood.exe. And after that, I'll put the name of the .par file. And by pressing enter, the simulation would start. These are the introductory steps of the code. And if we wait for a couple of seconds, the simulation should start. So the simulation is started. This is the first time step. So the first data is going to be written at the beginning, and if we let the simulation to continue, it will go one by one. So this is the second time step after an hour of simulation. So I'm going to wait until the simulation is finished and show you the results. When the simulation is finished, we can see that the output files are saved in a directory inside the main directory of the test case, and the results are saved in 2 different formats. The 2D results are saved with VTK format or extension, and they contain the 2D results in a multi-resolution or non-uniform grid format. We can use ParaView software to visualize any of these VTK files. So if I load a VTK file, let's say the first one, and click apply, it might take a couple of seconds because the files are heavy. So after the file is properly loaded, if we click on representation and choose surface with edges, we can see the generated non-uniform grid. And if I zoom in, you can see the multi-resolution form of the grid over the whole catchment. The other type of the data that is generated and we might be interested in is the stage file, of course, which is written in the text file format. And here we have only one stage point position, and therefore it's just one column data. So this was the simulation of the UpperLEE test case using lisflood-fp non-uniform grid ACC solver parallelized on GPU. And in the next video, I'm going to show you how to run another test case.